A circular loop of copper wire with a radius of 5 centimeters is at rest in a 2 Tesla magnetic field directed out of the page. The diameter of the wire itself, not the whole loop, but just the wire, is 2 millimeters, and the resistivity of copper is given as 1.68 times 10 to the negative 8 ohm meters. So for part A, calculate the total resistance of the loop of copper wire. The equation for resistance is rho L over A, where rho is the resistivity of the wire, which is given. L is the length of the wire, which if you think of this as one loop of a circle, it's the circumference, which the equation is 2 pi r. And I'm going to use a capital R to represent the radius of this actual circle, divided by the area, which is the cross-sectional area of the wire itself, which is pi little r squared. And I'm using the little r to represent the radius of the actual wire. And you'll notice in this equation you have a pi in the top and the bottom that cancel out to make things a little easier. So we're left with rho, which is the 1.68 times 10 to the negative 8 times 2 times the radius of the loop of wire, which is 5 centimeters or 0.05 meters, divided by the r squared, where r is the radius of the wire itself. The diameter was given as 2 millimeters, so the radius is 1 millimeter, which is 0.001 meters squared. And that will give you an answer of a resistance of 0.00168 ohms. For part B, determine the magnitude and direction of the current induced in the wire loop if it remains at rest in the magnetic field. The big thing to note here is that since nothing is changing, the magnetic field is not changing, the area of the loop isn't changing, the angle isn't changing, nothing's moving at all, the change in the magnetic flux is equal to 0. And if the change in flux is equal to 0, that means there's no EMF induced in the loop, and that means there's no current induced in the loop. So the I is equal to 0 since the flux isn't changing. For part C, determine the magnitude and direction of the current induced in the wire loop if the magnetic field suddenly doubles in strength to 4 Tesla in a time of 0.1 seconds. So Faraday's law for a single loop of wire is that the EMF is equal to the change in the magnetic flux over time. Since the area is oriented perpendicular to the field, that means we're going to get the maximum flux, so I can replace the magnetic flux with BA and leave off the cosine of theta. So delta BA over delta T. The area of the loop isn't changing, so I'm going to take this area out in front of that delta symbol. And I'm going to replace the area with the pi r squared. Keep in mind this is the capital R because we're talking about the area of that full circle. So pi r squared times the change in magnetic field over time. And now I can plug everything in. I have pi times the radius, which was 0.05 squared, times the change in magnetic field. The magnetic field was 2 and it went to 4, so that's a change of 2 divided by the time of 0.1 seconds, which is equal to 0.0785 volts. But the question is asking for the current, not the EMF, so now we have to use Ohm's law to get the current, which is the EMF over the resistance, so 0.0785 divided by the resistance, which you figured out in part A of 0.00168, is equal to 46.75 amps. As far as the direction of this current, the magnetic field in this case is getting stronger, which means the induced magnetic field is going to be in the opposite direction to cancel out that increase in magnetic field. So the induced magnetic field is going to be into the page, and using the first right-hand rule, if you put your fingers pointing into the page, your thumb is curling clockwise. So that means the induced current of the 46.75 amps is clockwise. And for part D, determine the magnitude and direction of the current induced in the wire loop if the magnetic field drops from 4 Tesla back to its initial value of 2 Tesla in a time of 0.5 seconds. So the EMF is once again the change in the magnetic flux over time. And what you'll notice in this case is that everything is exactly the same as before, except for the time, instead of 0.1 seconds, is 0.5 seconds. The change in the magnetic field is still 2, because we went from 4 down to 2. So I can use all the same stuff that I had right here, just changing the delta t from a 0.1 to a 0.5. So I have pi times 0.05 squared times 2 divided by 0.5 is equal to 0.0157 volts. So the current is equal to 0.0157 divided by the resistance of 0.00168, giving a current now of 9.35 amps. And this time, the magnetic field pointing out of the page is getting weaker, so the induced magnetic field is in the same direction, which is out of the page. And then using the first right-hand rule, if you put your fingers pointing out of the page, that means your thumb is curling counterclockwise, so the induced current of the 9.35 amps is counterclockwise.